Hello, this is video number 25 on my multivariable calculus course. In this video, we're going to talk about vector fields and some operations on vector fields and a very specific kind of vector field that is going to be very useful for us. What is a vector field? A vector field is a function that assigns vectors to points on the plane or in the three-dimensional space. So some examples of vector fields that appear in physics and engineering are electric fields, fluid flows, which means like basically the velocity of a fluid, and any type of force. So at any given point, we assign a vector. This vector could be a force, could be velocity of some sort. So if you have, let's say, a river, at any given point, there's a velocity for the particle at that point. So that's a fluid flow, and that's a vector field. So let's look at an example of a vector field from physics. Find a formula for the gravitational force for an object of mass m on Earth. So what is the gravitational force? We have a formula for the gravitational force. If this is the Earth, which I'm assuming this is a sphere, but it doesn't actually matter, and the center of the Earth, I'll place the origin at that point, and at a point x comma y comma z, I'm trying to figure out what's this gravitational force. So let's first find the direction of the gravitational force. So the direction is going to be towards the origin. So towards the origin means minus xyz. But because it's a direction, I'll have to also divide by its magnitude. So this is the direction of this force. Now, what is the magnitude of the force? Magnitude is evaluated by one of the laws of physics, which is gmm divided by radius squared, the distance squared, x squared plus y squared plus z squared. G is the universal constant, gravitational constant. M is the mass of the Earth. So this is the mass of the Earth. G is the universal gravitational constant. So universal uh, gravitational constant, and lowercase m is what they already gave us, the mass of the object. So in order to find the vector field, we'll have to take the magnitude and multiply by its direction. So this is the magnitude, and we'll multiply that by the direction, which is minus x comma y comma z divided by its magnitude. And we could simplify that into minus gmm times xyz divided by x squared plus y squared plus z squared to the power of 3/2. So this is the gravitational force. So this is a vector field. So here is the next example, and this example is from mathematics. So this is something we have talked about before. Let f be a multivariable function, then gradient of f is a vector field. So what is gradient of f? So if you look at the gradient of f, if f is a function of two variables, it is partial of f with respect to x and partial of f with respect to y, which is a vector field. So it assigns to every point xy the gradient. And if it's a function of three variables, then it would be partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z. So that is a vector field. Okay, now how do we do some operations on vector fields? The first thing we're going to talk about is the derivative of a vector field. So what is the derivative of a vector field? There are two different ways of thinking about derivative or rate of change for vector fields. The first one is called the divergence of a vector field, and it is denoted by div f. So that's the divergence of f, and the value is e sub x. So derivative of the first component with respect to x, derivative of the second component with respect to y, and derivative of the third one with respect to z. So we look at the rate of change of this vector field in each direction, and we add it up. And clearly that's a kind of rate of change. Now, there is a way to remember that, kind of a shortcut to remember this formula, and that uses this operator called nabla, which is, this is the Greek letter nabla, which is partial with respect to x, partial with respect to y, partial with respect to z. So if you find the dot product of this and f, that's the same thing as dot product of this operator and PQR. Now, this is just something very formal. It doesn't quite mean anything. It just means that you do the operation and then you add them up. So you do the second partial of p with respect to x, partial of q with respect to y, and partial of r with respect to z, and then you add them up. So it looks like a dot product. There's also another reason for us to use this notation, which we will talk about shortly. Divergence of f is, as we talked about, some form of derivative of a vector field. If f is a fluid flow, then divergence of f measures the rate of mass flow per unit volume from a given point. If your fluid flow is density times velocity, this is exactly how it measures, what it measures. It measures the rate of mass flow per unit volume from a given point. So if the divergence is positive, it means there is a mass flow coming out of the point. If it is negative, so this is positive divergence. If it is negative, it is going in. So that's what it means. Another kind of derivative is what we call curl of a vector field. Using the notation that we just talked about, curl is cross product. So let me give you the formula for curl. This is the cross product of nabla and f. So in other words, you'll do ijk and then partial with respect to x, partial with respect to y, partial with respect to z, and then pqr. So the first component is you multiply I by the remaining determinant. So you eliminate this column and this row. You get partial with respect to y, partial with respect to z, q, r. And then we do minus. So we eliminate the first row and the second column this time. So first row and the second column. We get minus j times partial with respect to x, partial with respect to z, and then p and r, and then plus k. Eliminate the first row and the last column. We get plus k, partial with respect to x, partial with respect to y, p and q. So what does that give us? It gives us partial of r with respect to y minus partial of q with respect to z, I, and then minus partial of r with respect to x minus partial of p with respect to z, j, and then plus partial of q with respect to x minus partial of p with respect to y, k. So this is the definition of curl. So we will do an example on this one. But before that, what does this curl mean? If you suppose that F is a fluid flow, so let's say it is the velocity of a fluid, then the particle in the fluid and the particles in the fluid rotate about the vector curl of F. So if you look at a point and let's say the curl is like this. So what does it mean? What does curl mean? It means every point, the objects around it, like the particles around this point, are rotating this way. So, and in fact, it satisfies the right hand rule. The magnitude of this is the rate of rotation. So the speed of rotation is in fact just the magnitude of curl. So the magnitude of curl of F is the rate of rotation. So let's look at an example. Find divergence of f and curl of f for this vector field. So we will go ahead and find the curl and divergence. Divergence of f is the dot product of the nabla and f, which is partial of the first component with respect to x, partial of the second component with respect to y, and partial of the last one with respect to z. So let's go ahead and evaluate these and add them up. Partial of that one with respect to x is 2x, partial of that with respect to y is negative z, and the last one is 2z. So the answer is 2x plus z. So that is the divergence. What is the curl of f? That is I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, x squared plus y minus yz, z squared. Okay, so let's evaluate this. So the first one is partial this determinant, which is partial of z squared with respect to y, that's 0, minus partial of negative yz with respect to z, so minus y. We'll have to multiply that by I and then minus. So the next determinant is determinant of this one. It would be partial of z squared with respect to x, which means 0, and then partial of x squared plus y with respect to z, that is also 0, times j, and then plus the last determinant is determinant of this one. So partial of negative yz with respect to x, that's 0, minus partial of x squared plus y with respect to y, that is 1, times k. So the curl is yi minus k. Okay, so this is the answer to this problem. Let's now look at two important identities. Two important identities that relate curl, divergence, and gradient are very useful. Curl of gradient is 0 and divergence of curl is 0 also. So these two identities are easier to remember using the notations that we saw before. So this guy is curl of gradient of f. Now, think about it this way. If you have two vectors, when two vectors are multiples of each other, they are in the same direction. Therefore, their products, their cross product is 0. So you can think about these two as multiples of each other. Therefore, the cross product would have to be 0. This is not any form of justification. It is just a way to remember that. Okay, this one is the divergence because it is the dot product of nabla, and then inside is curl of f. This is also 0 because, well, not because, but like a way to remember that is that every vector u dotted with u cross v is equal to 0. Why? Because u and u cross v are in fact perpendicular to each other. So a way to remember these two formulas is to just kind of use our intuition about dot product and cross product, the properties of dot product and cross product. Now these vector fields that are of the form gradient of a vector field are very important vector fields in math and science. These vector fields are called conservative vector field, and the function f is called a potential function. So any vector field that is of the form f sub x, f sub y, or f sub x, f sub y, f sub z is called a conservative vector field. Now, how do we know if a vector field is conservative? Well, the way we know is by taking the curl and then showing that the curl is equal to 0, and also making sure that our vector field is defined over the entire plane or the entire three-dimensional space. So let's do an example on this one. And this is going to be, these two are going to be the last two examples. Determine if each vector field is conservative. So how do we determine if these two vector fields are conservative? Two things. First of all, f is defined over the entire three-dimensional space. So the domain of f is the entire space. Next, we'll have to find the curl of this f, and that would give us the reason that we were looking for. So partial with respect to x, partial with respect to y, partial with respect to z. The first component is y e to the xy. The second one is x e to the xy plus cosine of y. And the last one is 1. So we'll go ahead and evaluate the curl. Partial of, so we have to do this determinant first. Partial of 1 with respect to y is 0, and partial of this with respect to y, z is also 0. So that is 0 minus 0I minus. The next one is determinant of this. Partial of 1 with respect to x is 0, and partial of this one with respect to z, y e to the xy with respect to z is also 0. And then the last one is this 2 by 2 determinant right here. So we'll have to do partial of x e to the xy plus cosine of y with respect to x. We get e to the xy plus xy e to the xy minus partial of this with respect to y, which is e to the xy, and then minus yx e to the xy, and then times k. And of course, all the components are 0, therefore, this vector field is conservative. Okay, so this is a way to check that, in fact, a vector field is conservative without having to find its potential function. Now that we know it is conservative, we can go ahead and find its potential function, because they said if it is, find a potential function. So we'll go ahead and find a potential function. So for a potential function, we need this. We need f to be, capital F, to be gradient of f, which means partial with respect to x would have to be the first component of capital F, which is y e to the xy. So this would have to be y e to the xy. Partial with respect to y would have to be x e to the xy plus cosine of y, and partial with respect to z would have to be 1. So here's how we're going to solve this problem now. We will go ahead and evaluate f from the first one. So f would be integral of y e to the xy is e to the xy, because when you differentiate e to the xy, you get e to the xy times y by the chain rule. However, we need a plus c, but because this is partial derivative, it could be a function of y and z that has been differentiated with respect to x, and we ended up with 0. Next, we're going to take that and plug it into the second equation. I'm going to name these equations. So we're going to plug it into the second equation. So we take the derivative of f with respect to y. That would be x e to the xy plus g sub y. That's equal to x e to the xy plus cosine of y. So that gives us g sub y equals cosine of y. Now we'll have to integrate again. So g of yz is going to be sine of y, but again we need plus c. But because this is a partial, any function of z would disappear when you take the derivative. So this is what we get. So this means f is going to be, f was e to the xy times x plus, or no, just e to the xy plus g of, so this is where I'm getting f from. It was e to the xy plus g. So we'll have to just add g to that. Plus sine of y plus h of z. And then we'll substitute that into the third equation. So by the third equation, we can say derivative of this with respect to z, which is h prime of z, is equal to 1. Now, if we look back and look at the problem is asking us to find a potential function. It's not asking us to find all potential functions. It's asking us to find a potential function. So we don't need a plus c here because we are looking for only one potential function. So z, f of h of z equals z works, which means I can find a potential function from here. So a potential function is going to be e to the xy plus sine of y plus z. So this is a potential function. Okay, next part of the problem. We are given another vector field and we are asked to check if it is conservative or not, and then they're asking us to find a potential function. So since this is a vector field in 2 dimension, we'll have to turn the third component to 0, because in order to find the cross product, in order to be able to find the cross product, we need to have a third component. This one doesn't have a third component. So what we need to do is to set the third component to be equal to 0. So curl of f is going to be I, j, k, partial with respect to x, y, and z. The third component is 0. The first and second components are x e to the x and y squared minus 1. So x e to the x and y squared minus 1. Let's evaluate the determinant. So the first one is this determinant, partial of 0 with respect to y, that's 0, minus partial of y squared minus 1 with respect to z, that's also 0, minus. So next one is also 0 minus 0, j. And the last one is partial of e to the x with respect to y, which is 0 again, and partial of y squared minus 1 with respect to x, which is also 0. So this is equal to the 0 vector. Also, this vector field f is defined, or its domain is also the domain of f is the entire plane. So that means f is in fact conservative. Okay, so what's next? Next thing is to evaluate its potential function. So assume that f is a potential function. So assume this f is equal to gradient of f. So what we have is partial of f with respect to x must be the first component, and partial of f with respect to y would have to be the second component. So we'll have to integrate the first one, plug it into the second one, and then solve for f. So we'll have to integrate x e to the x. So this is integral of x e to the x dx. Well, this is going to be equal to, and remember this f is a function of two variables, both x and y. So this is equal to, we'll have to do integration by parts. So u would be x, dv would be e to the x dx. So v would be e to the x, so this would be x e to the x minus integral of v du, so e to the x dx, which is going to be x e to the x minus e to the x plus a constant, but this would have to be a function of y because these are partial differentiations, not regular differentiations. Now we take that and plug it into the second equation. We get g prime of y equals y squared minus 1. So we can integrate and get one potential function because that's what they asked us to do. They didn't ask us to find all potential functions. They asked us to find one. So that means a potential function is going to be, we'll just plug this back into f. X e to the x minus e to the x plus 1/3 y cubed minus y. So this is a potential function. To summarize, we talked about what vector fields are, we talked about curl and divergence, two relations between curl, divergence, and gradient. We talked about conservative vector fields. Any vector field of the form gradient of f is called a conservative vector field. F, lowercase f, is called a potential function of capital F. And in order to check if a vector field is conservative, we need to make sure that it is defined over the entire plane, and also curl is 0. To find a potential function f, we set the system of equations f sub x equals p, f sub y equals q, and f sub z equals r. Solve f sub x equals p by integrating. Then instead of setting plus c, we set plus g of yz. Then you plug it into the second equation. Integrate, instead of plus c, set h of z, and then plug it into the third equation and get our final answer. Typically, we only need one potential function, so you don't really need a plus c at the end. I will see you in the next video.